In the previous module, we discussed the structure of the atom, specifically how electrons, in order to achieve a full outer shell, can either be handed off, collected, or indeed shared, forming ionic or covalent bonds, respectively. Acidity relates specifically to the concentration of H+. H+, of course, being an atom of hydrogen which has lost a single electron. Of course, given your understanding of the structure of the hydrogen atom, this results in H+, otherwise being equivalent to a single proton. This proton is often considered as H3O+ in water, where the H+ is transferred onto H2O. An acid is a substance which can lose one or more equivalents of H+, and a base is a substance which can pick up H+. If we look at the equation just below on the board, as you can see, we've shown a general formula for an acid, which is written as AH, or sometimes as HA. In the case of B, which is our example base here, you can see that H+ is transferred from the acid onto the base. This results in the formation of BH+, shown in blue, and the conjugate base A-, shown in red. Bear in mind that, as with all things chemical, matter is conserved, which means what is on one side of the equation must also be replicated on the other side of the equation, and that includes the balance of charges. When an acid, AH or HA, reacts with a base, H+ is transferred. And when we're considering acidity, we look at the concentration of H+, the concentration of protons in a given solution. Water, which is a universal solvent for the vast majority of ionic reactions, as we'll see in the next lecture, is considered amphoteric. The term amphoteric basically means that a substance or system or compound can act either as a proton donor or as a proton acceptor. And water is an example of an amphoteric compound. There are, of course, others which are ionic, and we may touch upon them a little later on. But for now, what you should be content with is that HA, our model acid here, can protonate H2O to give rise to H3O+, okay? Otherwise known as the hydronium ion. B, a base, can also react with H2O to give rise to the hydroxide ion, shown in red on the second part of that equation. It can also react with itself and ionize itself, forming a mixture of hydroxide and, of course, H3O+. As most acid-base reactions, as I've said, take place in water, it is common not to include the water directly in the equation. So you'll often see acid-base equilibria, acid-base equations, written as the following, where HA is shown to separate or lyse into A- and H+. And a base, shown here as a neutral species, although sometimes they are ionic and negatively charged, reacts with H+ to give BH+. So these are the two types of compounds or types of equations I'd like to introduce to you in this lecture.
You just completed your first video of the world's best medical exam preparation. Lecturio brings the knowledge of worldwide leading medical experts and teaching award winners to your PC, tablet, or smartphone. Prepare yourself and check your progress with thousands of quiz questions customized to USMLE standards. And the very best, you can get in touch with our medical experts personally. Visit Lecturio.com now and continue with the most inspiring medical education around the globe, anytime, anywhere.